In this demonstration, we're going to look at the light that's given off when we excite different gases with a high voltage. And this is going to be a lot like looking at a neon light, which is essentially doing exactly the same thing. So the way that we're going to accomplish it is to take a vacuum tube, in other words, a tube that might look something like this, just a glass tube, and they evacuate all the air out of it, and then inject it with the vapor of a variety of different elements. And so this is a different kind of tube that we can use in the lab, but the ones we're going to use for this demonstration are encased in plastic for more safety. I think you might be able to see the tube, just a little tube that's right inside there. This one in particular has hydrogen gas inside, and on the back, the way that we get it to glow is to send high voltage between these two electrodes that are connected on either end of this tube that is encased in plastic. And that is done using a power supply. That's this big black box. And so I can put that hydrogen tube in there and turn it on. You can see it gives a characteristic glow. So that's hydrogen. Let's just take a quick look at how it would be different if I put helium. Different color. Kind of looks like the sun. Makes sense? The sun is mainly composed of hydrogen and helium. So in turn, we'll take a look at these different gases that I have lined up here, but we're going to do something different. To really understand what's going on, we're going to look at these different gases when they're excited by high voltage and they emit light. We're going to look at it through something that's called a diffraction grating. And a diffraction grating is just a piece of plastic with lots of little grooves that are sort of scratched into it in parallel to each other. And so this is an example of a diffraction grating. You're going to have a lab on understanding how this works, but you can kind of see if I tilt it at the right angle there, you can sort of see a rainbow. And so just in brief, what a diffraction grating is going to do is take all the colors that are coming from the hot gas and break them apart so you can see them independently. So the way we can think about a diffraction grating and its usefulness to us is to consider the fact that whenever we look at a light source, so if you were to look at this hydrogen light coming from this hot gas of hydrogen, it looks kind of a reddish purple color. But the reality of it is we're going to see it's made up of only a few different wavelengths of light out of the visible spectrum. And so the problem is that your eye combines all the wavelengths and sends eventually through the different receptors in your retina a signal to your brain, and your brain just has to interpret that as one particular color coming from that point in space. It isn't able to break apart or determine what all the individual wavelengths of light or different colors are that go into making up this purple. So you can think about it like this. Here I've got some plastic sheets, and if you look at that, it looks green to us, right? But I think you can tell that actually if I take these apart, there is no green. There is literally no green pigment at all. That's just an artifact of how your eye combines blue and yellow and sends the signal, and your brain just interprets those two signals, blue and yellow, and calls it green, even though there's zero green coming into the eye from these two pieces of plastic. So this is what your eye sees. Everything's all blended together. If I were to place a diffraction grating in front of these pieces of plastic and it was bright enough, then what the diffraction grating does is sort of separate it. And so you would actually see the yellow and the blue as a result of going through the diffraction grating. So it allows us to determine what are the colors that go into making up anything we might see with our eyes. So it's much more powerful in a way than the eye is, because it's going to break that green into its component colors. All right. So the diffraction grating, I'm going to move that in front of the camera now. So here it comes. I'm placing it in front of the camera. And I'm going to turn the lights down. Now we're going to take a look and see what happens. So right away on the top, there's a little white light bulb. And up near the top, you can see a full rainbow going all the way from red over to blue. And that's characteristic of an incandescent light, something that's called a continuous light source that emits all the colors of the rainbow. So that looks white to us because your eye is taking all the wavelengths in the visible spectrum, combining them together in a signal, and your brain says that's white. But really, that white light is all of the colors of the rainbow. So now look down below. Here we're looking at hydrogen, and we can see that that color that we think of is a reddish kind of a purple is actually only comprised of what appears to be just 3 wavelengths of light. So if I take the diffraction grating off the camera lens, it's just a dark room, and the hydrogen light looks kind of that reddish purplish that we would normally see. So now the diffraction grating, when I put it in front of the lens, is going to separate all the different colors that go into making up that hydrogen light. And there aren't very many. In fact, to be honest, there's one more blue color, blue wavelength, that is a little bit farther to the left over there of the bluest one that you can see in this picture. But the camera doesn't pick up that color very well. I can actually see it if I look through the diffraction grating with my eye. Our eyes are more sensitive to blue than the camera is. But the main point of this is that you can see that that light from hydrogen is only made up of 3 or 4 different individual wavelengths or colors of light. And so that's really interesting. We have to think about answering the question, why does hydrogen only give off a few colors of light, whereas the light bulb above it gives off all the colors, visible colors of light? So that's a question that led to the great revolution in physics and chemistry called quantum mechanics. And so let's just take a look at the other elements and a compound that we have available and see, and you should make note of this in your notes what you're looking at. So we see that hydrogen, the light that hydrogen gives off is only comprised of 4 different wavelengths, one that you can't see on the camera, but it's there. It's a little bit more blue. So I'm going to swap this out, and we're going to look at helium. So remember the color of hydrogen? And I'm just going to turn up the sensitivity on the camera. So there's something interesting. Hydrogen is actually emitting different wavelengths of light than helium does. And helium here, we can see, has different colors, but they're not all of the same intensity. That sort of a yellowish gold, a green, and a blue one are the brightest, but the color that your eye sees, the color of the original helium tube over there on the left, is as if you could take all of those wavelengths that you see on the right, smush them together, and that is what your eye is sending to your brain, and that's the color that your brain says that it is. So helium looks kind of white in a way because it has most of the colors of the rainbow, but it's not as complete as the incandescent light on top. So now we're going to take a look at another element, nitrogen. This time it's not nitrogen atoms in the tube, it's going to be N2 molecules. So a little bit more complex than just atoms. And what do we notice? Quite a bit different. So you might want to make a note and record what you see there. So that is N2 gas. to do neon. You can think about what color you expect this to be. So that's sort of the neon gas tube, and you can see it looks an orangish red to us. And in fact, there's almost no blue light or green light. So neon looks at reddish orange, and it's not emitting any any green or blue light at all. It only emits red, and it's just a variety of different colors in the red and orange, but no blues and greens. So that was neon. Let's look at another noble gas, argon. So I'll turn up the sensitivity. This one's a little bit dimmer, but I think you can see that it's a different set of lines. And here we see argon as opposed to neon. Argon looks nice and purpley. It's got a lot of blue, and it's got bright lines there in the red, and so it kind of gives us, our brain thinks, smooshes it together and gives us that purple color. So let's do one more. Let's look and see what happens when you put carbon dioxide. So that one is very complicated. It looks really white. A little bit more on the blue side. Let me turn down the sensitivity. So it looks close to white, but if you look at it, it's kind of a bluish white color. And you can see, while most of the colors of the rainbow are there, it's very bright in the blue, the green, and more in the orange, and not as bright in the red. And so that's why this white light looks a little bit bluer. So what's the takeaway from all this? When we look at elements, we see only very specific colors, and each element is different from other elements. And so we have to answer that question. If I look anywhere in the universe, hydrogen will always give me the same 4 wavelengths. If I look anywhere in the universe, carbon dioxide, when excited, will always give the same spectrum that you see here. And actually, this is a way that we can detect elements and compounds out in space, because not only can the elements in the gaseous state in space be excited by high voltage, they can also be excited by light from a nearby star. And so the way that we know what's in the distant stars, and they're working on figuring out what elements are in the atmospheres of exoplanets, those planets that have been discovered around other stars, is to look and see what happens when the starlight shines through those gases, excites them, and when it hits Earth, we can run them through a diffraction grating, look at the lines, the colors that make up that light, and match it to the elements and compounds that we already know. And that's the way that we can tell what are in objects millions of miles, light years away. So it's a really powerful tool. So here's something else you should notice about what a diffraction grating does to the different wavelengths of light. You should notice that in a very repeatable way, blue is always closest to the original light source, and red is farthest away, with the other colors of the rainbow in between. So on the left here, I have a strip of different colored LEDs, and it's a little oversaturated because they're so bright for the camera, but I'm going to turn the white light away. I want you to look on the right-hand side of the screen. We're now looking through a diffraction grating. So look where the colors are relative to their position close to the original light source. So the blue LED is at the top, and you can see that it's actually comprised of blue, and there's a little bit of green in there too. But you can see the blue is closest to the original light source that we're looking at through the diffraction grating. And at the very bottom is a red LED, and that's giving off red light that's far to the right. And the other LEDs in between give different colors, and they're just broken apart and spread out by that diffraction grating at different distances from the original light source, and we're going to investigate why that would be true. It's related to the wavelength of the light.